All right, going to start chapter 17, current and resistance. It only has 3 sections in it, so we'll see. Today we're going to go over 17.1 through 3, electric current. We're just talking about the current I. So we'll calculate current. We'll talk a little bit about drift speed. Your book goes into a lot of calculation of drift speed, but that's not really on the AP test, so we'll talk about it. But I'm going to try to avoid most of the calculations for it. Not that it's hard, you just plug the numbers in, but it's not really relevant to what we're learning. I mean, it's relevant, it's just not tested. Okay, and then we'll talk about potential difference, which chapter 16 is all about potential difference. It goes into like really big detail about potential difference, and all you need to know is what I teach you in like one slide here. So there's no reason to cover that whole chapter when I can cover it in one slide. So current and charge. Current is a rate at which charge is going to flow through the wire. So if charge is just like electrons moving, then current is just how much electrons are moving over a certain amount of time. So current is always going to flow perpendicular to the surface area of the wire. So I have this funny little circle here. If this is the surface of the wire, then the current is going to flow perpendicular out of it, so it goes through the wire. This would be a really big wire. Nobody has cups. I know. I'll just talk and talk forever. And just flip through them like a college class. We're preparing for the real world here.
You better set it down gently.
Sit down hard. Thank you. Oh, what are those?
Colors. Pink, magenta, and yellow make red. Yellow and blue make green. Magenta and blue. No, this is cyan and magenta make blue. And we have all 3 of them.
Makes.
With the art code. We get black.
If we hold it in front of the screen, we should.
Well, there's a lot of green light going through there, so I don't know what you're need a lot.
Whoa. Psychedelic, man. Whoa, the yellow one can be.
Well, the yellow's solid.
No, it's not.
I'm doing light in my other classes, that's why I have this stuff out. Okay, moving on. We're ready? We're ready? Yep. Okay, so here's your equation for current. Current is capital I. It's measured in amps, which is a capital but little a, just like Newton's is a capital N, but it's usually a little. And it's the change in charge over the change in time. Just like if you were thinking about velocity, it's the change in distance over the change in time. Charge is the same thing. It's a rate of charge. Current is the same thing. It's the rate of charge.
This is only 26 volts.
What current? Why do we have calculation? What else do we use for it? Circumference? That's it. Use that. We use I for like
Coulombs.
things already.
Yeah, coulombs.
But you could do a fancy C. Yeah. You could do a fancy C like.
Take it up with the gods of physics.
That's true.
I just report the material. I don't create
Wait,
it.
who created physics?
The gods of physics. Who created physics? Lots of people.
Darn, it's not like calculus.
I mean, you can blame it on like Newton, kind of, but that would just be the mechanics.
Well, Newton did create calculus.
Well,
But he invented calculus to explain.
That's true.
Yeah, so it came in hand in hand.
Yeah.
a lot of stuff already has.
We were learning on Western State.
Okay, now this is going to be average current. This is what you'll always be asked for, but if when you take higher level physics classes, you're asked for instantaneous, you take the derivative of the current with respect to time. You could also do the limit of that according to the derivative. When the current is steady, which is what you guys will be working with, this is a fine equation. It's just the average of it. When it's steady, though, the average and the instantaneous will be the same. But you don't need anything more than this. This is fine. Okay, direction of current. current is weird. We would think since charges are electrons, right, and then just like missing electrons, that our current would be the direction of flow of electrons. That is not true. It is backwards. Direction's positive direction is the flow of the positive charge. So if you have electrons moving through your wire, here's our wire, and our electrons are happy and going this way, our current will be in the direction of the positive way, in the opposite way which the electrons are moving. Which, when it comes to mathematics and just thinking about charges, positive, negative in general, it's fine because, remember, charges, negative and positive, are talking about the charge themselves, whereas with vectors, negative and positive is talking about direction. So charges and directions should not be crossing any wires. But if you just treat it mathematically, it will be fine. You just need to know in the back of your head that just because the current's this way, that means the electrons are flowing in the opposite.
You made it fun. Charges and directions shouldn't be crossing wires.
Yes.
Why?
So this one's just like a little, and they'll throw a trick question in there, like a conceptual question, and they'll be like, if the direction of the charge is north, which way are the electrons traveling? And you'll be like, south. Because opposite direction in which the current is flowing. Because the electrons, even though there's nothing actually flowing that way, it's just weird. It's weird. And they will trick you, so just pay attention.
I just need to be super sassy and have incredibly green shirts.
All right. Drift speed. Here's our little thing about drift speed. Electrons don't really move in a straight path. They're electrons. They're all over the place all the time. And that comes down to we don't actually know where the electron is because of the, I can't think of it.
That one guy's principle
The
that
momentum and the electron and the speed.
Electron cloud.
Those are the law.
You can know the mass of an electron.
Starts with an H.
Yeah. Heisenberg?
Heisenberg, thank you. Heisenberg principle.
That's
I
right.
couldn't get Higgs boson out of my head. That's all I could think of. Heisenberg principle says you can't know the location and the momentum of the particle at the same time. You can know, if you know one, you will not know anything about the other.
Cool.
So you can only know both with some sort of accuracy-ish.
Guesstimation.
It's not really a guesstimation. It's like the accuracy goes down.
It's moving so fast you can't pinpoint one, but if you pinpoint one, the other one doesn't exist.
Yes. But think about it as accuracy. The more accurate you know one, the less accurate you'll know the other. So you can know both with, a little bit of accuracy. All right, so this is like a path of an electron, zigzaggy all over the place. But when they say drift speed, we're looking at like about where the electron is going. So we can say the electron's pretty much going this way, and that's what's making up current. Is the electrons aren't just flowing straight through like we'd like to imagine. They're actually kind of all over the place, but overall, they're going that way. And that's what they mean by drift speed. I mean, which ways are the electrons mostly going? And, they're going to be mostly going some direction, and if they are moving some direction, then that's going to be our current. Remember, current is the electrons moving. If the electrons aren't moving, you don't have any current. Now, there is an equation to calculate this drift speed. I'm pretty sure I kept them out of all of your homeworks, but I might have missed one. So if you really need it, it is in the summary part. You can just go in and plug the numbers in. It should be hard. All right, voltage. This is the part that we kind of skipped this chapter 16 because it goes into like super detail, and I really didn't want to cover that because you don't need all of that. But voltage or potential difference is delta V. A lot of times when I write it, because I'm a little bit lazy, I just write big capital V, voltage. V equals IR, even though it should be written as delta V. So delta V. And the reason that I don't really deal with the delta V part is because usually it just says the potential difference is 4. It doesn't say that the potential difference change in the potential difference. It's not going from like 4 to 6, and then you have to go 4 minus 6. It doesn't really deal with that very much. Like when we're talking about velocity, it has delta x over t. The delta x, we're usually going from 0 to 4. But the t is, even though we're starting at 0 seconds and going to 10 seconds, it's usually just 10 seconds because we usually start at 0. With potential difference, they're not really saying where we're starting, where we're ending. We just say, oh, the potential difference is 4. So that's why I don't really put the delta part in there, because it's just like an extra step that a lot of times will confuse you, because you're going to be looking for an initial and final, and there really isn't one in these problems. So write it as capital V or delta V. Delta V is what you're going to see on the AP test, but we're just going to treat it like it's a single voltage. Now remember, potential difference is voltage. In your questions, sometimes it's going to say voltage, sometimes it's going to say potential difference. Same thing. Okay, what is potential difference? Potential difference is what kind of gets the current going. Think of it as a hill. And your electrons, if they were no longer charged particles and just had mass, they're going to flow down a hill. So potential difference is saying, here's our high part of our hill, here's our low part of the hill, and it's going to cause the electrons to move down. And that movement of the electrons, that's your current. So think of it as a hill with a stream going down it, and your electrons are flowing down the hill. So the potential difference says what is the difference between the hill heights. And that is going to tell you how fast the electrons fall. So it's kind of like a force pushing the electrons along, which potential difference can be related to the electromotive force, which we'll talk about a little bit in the next chapter, kind of.
But it's more like water flowing into an opening.
Right. Yes.
So if potential difference is high, and the electrons are going down, and the current
Don't worry about direction again. We're just trying to figure out what potential difference is. And what you have stated is true with the math, but I'm just trying to talk about what potential difference is. Because if we start to expand our this picture to like everything part of it, like what you just said, the current is going uphill, it's going to fall apart and it's not going to work. So I just want to look at specifically potential difference from here to here. But if we said the current was flowing down, then the electrons would actually be going uphill. So we'll just leave that out of the picture because it just doesn't
like
work.
this, like on a low hill, the electrons roll very slowly because they don't have very much movement. But on a high hill, they roll faster.
And that's the only part that we're looking at, just that, not having to do with the current or the direction. Yes, you are right, but that was where my picture breaks. Okay, so what is the potential difference? If you look at a battery in a circuit, you have a positive end and a negative end. That's their potential difference. The current is going to flow around from the positive to the negative. Now remember, the electrons are negative, so they're actually going from the negative side to the positive side, even though the current's going from positive to negative. Good? Good? You're okay with that? That's like the main, that's voltage. All right. So we're talking about a battery when we're talking about potential difference. Whenever you're trying to figure out, okay, what's my potential difference? A 6-volt battery, a 9-volt battery, double A's. There's some sort of voltage with that. That's your potential difference. Anything that's potential difference is going to be measured in volts. It's a capital but little v. So we've learned about amps and we learned about volts today. Let me put that on here. This one's in amps. And I is going to be in, yeah, messed that one up. One sec. Switch them.
It's over here by the flashlight.
There we go. Now it's right. So it's capital, but it's little, like newtons. It's capital, but little. Okay, so potential difference creates a change in charge across the negative to positive terminals. So when you hook a wire around it, those electrons are going to march in the direction they're supposed to because of this. They're going to march downhill. Right?
So what happens when a battery runs out of juice?
Runs out of juice?
Yeah. Is that just
This hill, over time, the chemicals that are causing that electric difference run out. They can no longer do their chemical reaction, I believe. And this is chemistry stuff, and fatty chemistry stuff. but they stop doing their chemical reaction, so the positive and negatives get closer until they're the same charge, and there's no charge difference.
The enzymes that create the catalyst, so every time that you have a different component, the enzymes change shape, and they can only, like, if you take two different particles, you put it in one enzyme, after it's done with the reaction, the enzyme is shaped differently, and the enzyme can only fit the shape. Like, it will only, like, start the reaction if it fits perfectly.
Yeah, so it's pretty much like, got everyone in here with them. Okay, thank you.
All right, to calculate this potential difference, this equation you're not actually going to use in your homework, I don't think. I think maybe one of them. But it's going to be your potential energy, your change in potential energy. So remember, change in potential, that could possibly be work when we're talking about mechanics. We don't usually use work here when we talk about electricity. But the change in potential energy over the charge. I don't think you use this in your homework, but you might use it later. Again, the AP Physics 1 test really only covers your very basic circuits. They do resistors and parallel and series circuits. So what I'm gearing you up for, and you learned electric force, and now you're just going to learn basic parallel and series circuits, but you need to know this stuff before we get into that. And that'll be next chapter, is just circuits. So your potential, V, this voltage is the potential difference. It's measured in volts. Your potential energy is measured in joules, just like all other potential energy. And Q is going to be the charge in coulombs. All right. A circuit is a closed loop. So if you take the battery out of your clicker is not going to work anymore because it doesn't have a closed circuit. You could put one battery in, but the circuit is still not closed because it has to take two batteries to complete that whole circuit the way it is. Now, some electronics, you can put one battery in and it'll work, and that's because it's wired differently. So that it does have a closed circuit. Think about Christmas lights. In some of the Christmas lights, you take the light out and the whole thing turns off. In some of them, you take a light out and they all work. That's just how they're wired. It's whether it's series or whether it's parallel. So the ones where you take it out and the rest of them stay on, those are closed loops. Ones that are, you take it out and all of them die, you've just broken the loop in that one. That would be a series. So these currents, remember, they have to flow from potential difference. So if you break that circuit, you no longer have this potential difference. You don't have a positive to a negative. You've killed that hill. You've obliterated the hill. So these electrons, they can't move because they can't march down the hill anymore. So your circuit doesn't work. And this flow of charge into like a light bulb is a flow of energy to the light bulb. So if the electrons don't move, then there's no flow, so the light bulb cannot emit energy. And we'll get more into that when we talk about resistance. What do you do? Okay. There's a couple of meters we're going to talk about. We're going to use this a little bit in our lab. We have our... I actually stole this PowerPoint, this slide from Eclipse PowerPoint. So meters in the circuit, ammeter. This ammeter measures amps, right? So that's current. To measure current, it has to be in line with what you are measuring. So if you have a circuit of a battery and a light bulb, you need to break the circuit up and put the light bulb in with the battery. And we'll talk more about why you have to do that in the next chapter, but you can just write this down for now and we'll use it later. So this one's the ammeter, and we have batteries and a wire. You can ignore this for now, we'll talk about that on the next slide. Then you have a light bulb and a wire. And then it would just go with another wire all the way back to the battery. So you have just a battery and a light bulb. So in order to measure the current of this, we just need to break that circuit and put it into the ammeter. So now you can measure it. And as you'll find out when we're talking about circuits in the next chapter, the reason that we have to do this is because current is constant in series. All right, next one is the voltmeter. It measures volts, which would be your potential difference. This one is opposite. It is now going to be connected in parallel instead. So what you do is you act like kind of like a little probe. You're like, oh, what's the potential of this? So if you want to find it over the light bulb, you put it on one side of the light bulb and then the other. So you just kind of, you don't have to break the circuit or anything. You just like test it. Like, what about here? What about here? So you could see our ammeter here. Now we got our circuit with the light bulb and battery. And then our voltmeter, we just put it on either side of what we want to measure. What is the potential difference from here to here? And if we wanted to find it for the battery, so let's say we had a 9-volt battery in there and we wanted to test, is it still giving out 9 volts? We just pick up our little probes and we put it on either side of the battery. Is it 9 volts? And you'll find that a lot of times they're not. Most of them are brand new. And again, you'll learn this in the next chapter, but I'll just say it here. The reason that voltmeters are measured in parallel, so like little probes, is because voltage is constant in parallel circuits. But we'll go over that later. And why I got these nice little pictures up here. This is kind of what it would look like on your workbench. This is called a circuit diagram. All right, current and charge practice, and then we'll get to some boring clicker questions. Wire has a current of 2.3 amps. How many electrons pass in 15 seconds? This is so easy. I don't even know what to do with it. Okay, so it's 2.3 amps. I. And 15 seconds? What are we looking for? Number of electrons. That's a little bit different than Q. And that's why I picked this one, because it's just a little bit more. Okay, what's one equation we want?
One that we did with
I
amps.
equals Q.
I equals Q over T. All right.
All right.
So that'll get us Q.
Then take n times 1. Then take n times 1.6 times 10 to the negative 19 equals whatever Q happens to be.
Good. Okay. So this is the number of electrons times the charge of an electron will give us the charge that's up here. Good. So when you come across these problems, that's how you do it. Because you're looking at charge. You don't even have to do the mole thing or anything. I think one of your problems has a mole in it, but this one, number of electrons times the charge, will give you your total charge. So let's put this in. We got 2.3 equals Q over 15. Don't ask me to try to do math in my head, but you end up with the wrong number.
That's a lot of electrons.
34.5, which is equal to Q. We'll plug it into this equation here. So N is going to equal divided by 2.16 and 10 to the 20. Is that what you guys got?
Yeah, I just went 2.2.
Yep, that's fine. Oh, and a heads up for your AP exam, most of the time, the significant figures are 3. Most of the time. But it will only affect you on your free response. So if you're not sure, use 3. Sometimes it's 2. But do not put all of the numbers in. If your calculator is showing you like 10 numbers, don't do that.
All they do.
Is that why I missed?
No, they don't. They want you to use significant figures, and it will take, it's worth 1 point, but if that's 1 point you can get, that's 1 more point towards your passing.
Is that why I got some wrong yesterday?
Mm-mm.
Oh, okay.
No, with my significant figures are set pretty low. Usually if you have the first 2 numbers within about 0.3 of the second number, you're good. Okay, any questions on our problem? So we got our first clicker question here. I did not go through the clicker questions very well yesterday because I was trying to finish this PowerPoint super quick. So I apologize if they're terrible. But I did take time on the test, so hopefully it'll be fine.